In this activity, we're going to establish a useful identity for understanding how a transfer function and the reciprocal of that transfer function are related in terms of their Bode plots. And this becomes useful in being able to establish connections between a zero and a pole and how they affect the overall Bode plot in different ways. We've actually already seen an example of this between the transfer functions s and 1 over s. And so let's go ahead and establish this. So assume that you know the magnitude and phase of a particular transfer function g of s evaluated I omega. So let's say that that's m and phi. And so now what we'd like to do is express the magnitude and phase of h of I omega, essentially these two quantities, in terms of the magnitude m and the phase phi. And then also think about how does that affect the decibel version of the magnitude. So go ahead and take a look at this, and then we'll go through my solution. All right, so the problem said that we already knew these values, and these are the magnitude and phase of a transfer function g evaluated at I omega. So if we now know that h is just the reciprocal of g, then when we evaluate h at I omega, we also get 1 over g at I omega. And so if we rewrite what g is, it's going to be the magnitude, its magnitude, multiplied by e to its phase, right? And so if we plug that in to our expression for h at I omega, then we can just represent this, this down here. This is really 1 over me to the I phi. So if we simplify that and break that up into the magnitude and phase, so again, kind of thinking about having a complex value in the denominator is not a good idea. We need to separate it out. The way we do that is we see that if we pull the exponent out like that, then we need to negate the phase in order to do that. And so that means that the phase of h is just going to be the negative of the phase of g. And the magnitude will be 1 over the magnitude of g. So the magnitude of h is 1 over the magnitude of g, and the phase is the negative. And so what does that do to the decibels? We plug that into our formula. It's 1 over the original magnitude, and so that can be expressed as essentially the same thing as this, is saying g I omega to the -1. And so that allows us to take that -1 and bring it down in front, and so that's why we get this negative. So essentially in the log plot, the decibel plot of the magnitude, you also get a negative sign. So this is one of the another elegant property of the writing things in decibels, is that now we're negating the phase and we're negating the magnitude in decibels, and that's how you express the reciprocal transfer function on the Bode plots. So I encourage you to go ahead and do this example also from kind of first principles, the same way we did the one we did before this, which was the pole version of this same transfer function. But now it's useful to use the result from our last activity. So in our last activity, we said that if these two transfer functions are related as reciprocals, then essentially we negate the phase and we negate the dB magnitude. And if we look at the magnitude directly, it's the reciprocal. So that means that our new magnitude is 1 over our old magnitude, which is simply, instead of having a negative up in the exponent, now it's just the same quantity to the 1/2 instead of the -1/2. And so then in the dB magnitude, we get this plus sign where we had a minus sign before. And then finally, on the phase, we just get a negative thrown out in front. So if we were to sketch these out, again, we would sketch essentially at low values of omega and large values of omega. So in this case, at low values of omega, again, this second term is not important, and so essentially you get 0. And so again, we get 0 at low values of omega. At large values of omega, we go through the same algebra to get the fact that this goes like 20 log omega plus 20 log tau. And the important part here is, again, this bit, and now it's going at plus 20 dB per decade, essentially. And so that's why these are now positive slopes for all of these different large omega values. And again, just like before, the transition happens at 1 over tau, where omega is about 1 over tau. And so that's why right here, this is the transition point for tau is equal to 10, right where the frequency is 0.1. In the phase, essentially we can evaluate again. We're going to get essentially the opposite. So this is going to, at small omega values, the negative of it, at small omega values, this is going to be slightly negative. Again, the same logic applies. Essentially, come up with this small omega value, a value of 1, and that produces something that as omega gets very, very close to 0, this becomes essentially just 0. Negative 0 is 0, so we still start at 0. But then what happens when omega is large? When omega is large, this becomes very, very large. Again, you get something that's very, very close to minus 90, but then you have this extra minus sign, so it flips it into a plus 90. So as omega gets large, you go to this plus 90 limit. And then the break-even point again is where that's 1 over tau, when omega is 1 over tau, and that gives you overall a plus 45. And so again, we can use those same ways of sketching to figure out the overall picture of this Bode diagram. The other thing that we're going to observe, though, is that by negating these two things, we're negating the dB magnitude and we're negating the phase. And so what ends up happening is that flips it over the zero line. So in this case, these two 0 lines, if you flip this vertically, both of these plots vertically, you'll observe that you get the exact same plot that we had for the pole case. And so visually, when we take the reciprocal, visually what that appears on the Bode plots as is that you're flipping over this 0 dB or the 0 phase horizontal line. So you're flipping it vertically to produce the new Bode diagrams. And so that's a great way to kind of intuitively and visually remember how these things relate. And this becomes important because we're soon going to be adding these things together where we'll have some poles and some zeros, and you'd like to combine the effects of all of these things. So whereas this gave a phase lag, essentially something between 0 and minus 90, this is giving a phase increase. In this case, you're keeping the same amplitude as the input at low frequencies, and then at high frequencies, this is actually amplifying, so the output is getting bigger compared to the input signal. And so that's what a 0 does, whereas a pole does the opposite.